All right. So today we're going to talk about the Biot-Savart law, also known as Biot-Savart for people who don't believe in the French, which is how we actually calculate magnetic fields due to a current distribution. So if we remember, when we started with E fields in calculus, we had these continuous charge distributions. We know E from a small point charge is k dq over r squared r hat. We added all those up after chopping our distribution into all these little charge segments, and then we got our answer. So similarly, we can define a magnetic field contribution as the sum of all of these little contributions using this Biot-Savart law. So we actually have not started from this because if you remember, the only thing we looked at with B fields so far was this B from a current carrying wire, which we just sort of took as a fact. So if we sort of go through this formula of the Biot-Savart law, we see that magnetic fields are generated by currents. There is an inverse square law dependence, but there's also this factor of sine theta that sort of differentiates it from the E field case. And if we think about it, that's how we encode the right hand rule. Because we said that magnetic force sort of follows this cross product Lorentz force. And also, if we remember how we dealt with the current carrying wire, we said that the field sort of wraps around the wire using this right hand rule. So this sine theta term is how we account for that, how B is going to be generated perpendicular to both the direction of current flow and perpendicular to the direction of the observation point. So this sine theta, it's really important that we don't actually get to pick the theta here. Like we've had some freedom in the past. This theta has to be between your current segment and your r vector or your distance vector. In most cases, this will work out to either be 90 degrees, this theta, or it's something that you can easily substitute away. And most of our contributions are going to be entirely into the plane or out of the plane of the page, so you don't have to tack on extra trig functions. But if you have something where you want only a part of the field, you will have to use an additional trig function. So our formula here for using Biot-Savart is chop up our distribution into current segments, define your sort of distance unit vector, figure out what sine theta is, as well as what the square distance to each segment is. And also, just by doing some right hand rule at different points, figure out if you need components, and if so, tack on another component maker. And then we integrate all the dBs to get our field. So the easiest case of Biot-Savart is just a current loop. So let's say that we have a counterclockwise current just circulating around a loop of radius r, and we wish to do this with Biot-Savart. So again, to find the direction, we pretend that each little piece is a wire to get its field. So if I'm at this top point here that where the current is indicated, if I stick my thumb in the direction of current flow and then wrap my fingers towards the center, we see it pops out of the page. And this argument works no matter where I'm at around the loop. So no matter where you're at, if you stick your thumb in the direction of current flow and wrap your fingers towards the center, they'll pop out. So no components are needed. We're going to generate an out of the page B field. And sometimes we just took that as a fact that if you have a counterclockwise current, that's going to generate an out of the page at you B field. But that's sort of how we justify it. Okay, so we're going to draw ourselves a current segment as well as its corresponding unit vector. So let's pick the one that's already labeled, this radius that's already labeled. So again, this is a circle. So a small current vector, IDL or just DL, it's up to you where you want to include the current, is going to look like that. And then our distance vector points, it's that distance vector between our observation point here. This is going to be our R. And notice that we do have something very nice happening because this is a circle. So one thing that makes the circular loop really nice is we see that this theta, which is by definition between our current segment and our radius, is 90 degrees. So what is the direction of the magnetic field at the center of the loop? Well, we just said using right hand rule, no matter where I stick my thumb around the loop, because it's going counterclockwise, it's always directly popping out of the page at the center. So this is out of the page. Are components needed? No, because we said that every single current distribution part is generating an out of the page field. So no, because all current segments generate a magnetic field contribution dB, which is out of the page. So there's no extraction because there's no canceling, it's pure addition. All right, let's figure out what r squared are and sine theta. Well, this one's really easy because we have a circle. So our distance r is just going to be equal to the radius of the loop. So r squared is just capital R squared. And then we can deal with sine theta. Well, sine theta, by definition, is the sine of the angle between our current segment and our observation point, and that is clearly a right angle because it is a circle. Because remember, if we define circular motion, we said our velocity was always going to be tangential to the circle, which is perpendicular to that r vector. So this is sine of 90 degrees, which is just 1. So we know that sine theta is 1. And this will just help us build our integral. So again, I scaffolded it this way so that we can see all the different Biot-Savart quantities that we have to plug in for. So let's do it. We said that B is equal to mu naught I over 4 pi times the sum of all of the dl sine theta divided by r squareds. And if we actually go through and do that, we see we have quite an easy integral to evaluate because we don't know anything about dl, but we said sine theta was 1 and little r was just capital R. And nothing in here varies, right? Because this capital R is a constant, 1 is of course a constant, so we get mu naught I over 4 pi capital R squared times the integral of dl. So now we're just thinking, what happens if we add up all the dl's, all the lengths of our current segment? Well, we have a circle, and the length of a circle is, of course, 2 pi r. So we just get mu naught I over 4 pi r squared times 2 pi r. And we get a similar looking result, but not quite. We get mu naught I over the pi's cancel, so we actually get 2r. So actually compare this with b from a wire. We said b from a wire is mu naught I over 2 pi r. So of course we get that same functional dependence as the wire, but the fact that it's circular removes the pi from the denominator, which I always thought makes sense. So this becomes a result that I do suggest we memorize, although the derivation is not that bad, because it's so similar to that wire formula you'll have memorized anyway. And now we'll use a sort of symmetry argument without performing any additional computations. What's the magnitude of the B field at the center of a semicircle? Well, this is not a component-related problem, so we don't have to complicate this, right? Because every time I stick my thumb, it's going to pop totally out of the page like that. So there's no components needed. So this is just as simple as B of the semicircle is just going to be 1/2 of B of the full circle, because all current segments are doing the same exact effect towards the center by symmetry. So mu naught I over 2r. So instead of mu naught I over 2r, we get mu naught I over 4r. So I always suggest we just know the loop formula. That's the one that we should know or know how to derive, and we can come up with these sort of children of the loop pretty easily with symmetry. Because all these little dBs are going to be equal. It doesn't matter where on the circle I am because of that symmetry. So if I have half the wire, of course, I'm just going to have half the B field. All right, so here's our formula. mu naught I over 2r. So again, realize that b from a wire is mu naught I over 2 pi r. So it's very similar, but not exact. Lots of multiple choice items will confuse these two because that makes a good distractor to use the wire formula on a loop. So of course we can just use symmetry. So b is just half of the loop in this semicircle case. All right, so we have a couple quick current distributions to deal with here. So these are all loop adjacent problems. So we're going to say that we know this formula as a fact now, and we're just going to use that to solve these problems. All right, so we got these concentric loops here. We have a counterclockwise I here. So either using the right hand rule or just using the fact that we know what counterclockwise currents do, we know that my inner loop is generating an out of the page B field. I like to actually write it on the figure just to manage it. And then outside we have a bigger loop carrying the same current, but that's going clockwise. So again, if I do that and try to wrap my fingers around this time, it's going into the page on the inside of the loop. So we are going to get a subtraction here. And also we know the B field should be out of the page because it's the same current, but it's more tightly concentrated in this center loop. All right, so as with any sort of field problem, we know that our B net is going to be B from the inner loop plus B from the outer loop as vectors. These are both full loops, so I can use the full loop expression. So mu naught I over 2r, and that points it out. And then mu naught I over 2 times 2r, which is going to be in, right? So just justifying that, we have a double the radius, and we also know that it is into the page. So we get mu naught I over 2r out plus mu naught I over 4r in. So this is a subtraction. So we have a half minus a quarter. So that is 2/4 minus 1/4, which is 1/4. So I actually get mu naught I over 4r, and the winner is out of the page. So that's a pretty standard question. All right, so now we can spice it up a little bit. There's not too much spice we can do with Biot-Savart without it being extremely frustrating, but here we have the rainbow. So this is a single closed shape of current. So if we track our current around here, we know it's going to start sort of in that clockwise direction. It wraps around and then comes back the other way. All right. So first of all, we can justify that the only things that actually matter are these two arcs. And that's because if we try to do the right-hand rule, we know that in order for a magnetic field to be generated, you need to have some sort of perpendicular component between your R vector and your current, because magnetic fields don't exist parallel to their current source. They have to loop around them. And how do I loop around something I'm parallel with? I can't do that. So these don't actually do anything to contribute to our net B field. So then we'll just take the same approach as last time, and I'm going to color the currents again just to help. So we know this current, this purple one, that's a counterclockwise current again, so that pops out. And then for my outer arc, we see that's going to be clockwise, generating an into the page current, or field, sorry. All right, and also just based on the shapes of these, it was given in the problem, these are all circle segments, so these are semicircles. So once again, I do know that my B is going to be B from the inner loop plus B from the outer loop. And these are semicircles, so I have to remember to half it. So for my loop of radius A, it's mu naught I over 2A, and that is a out of the page B field. And then same thing, I want half of a circle of radius B for my into the page B field. And now we see that everybody has a mu naught and a 1 over 4 when I put the 1/2 in that denominator. So this just gives mu naught I over 4, and then 1 over A minus 1 over B. That's going to be an out of the page field. And we can justify we didn't make any mistakes here because A is the inner radius. So A is smaller, which means 1 over A is going to be a big number compared to 1 over B, which is going to be small. So I'm doing big minus small, which is positive. So I am getting an out of the page field, as expected, based on the right hand rule. All right, so the main task of Biot-Savart, in addition to the loop, is being able to derive the wire formula, or at least set it up. So we know what we're expecting it to be, mu naught I over 2 pi r, for a long wire. So here we're just looking at a point along a perpendicular bisector of just a wire with length. So as per usual, we're going to define all of the normal quantities here. So we're just going to draw ourselves a current segment, and then we're also going to draw ourselves an r vector. And then we know that the theta is forced to be the angle between the two. So I don't have freedom of picking a theta I like. It has to be the one between your current segment and that. And technically, it should be probably the other theta. If we're being real textbook, like we might want that theta, but there's a nice property of sine that makes that not relevant because sine of the supplement is same of the sine of the angle. All right, so of course we got a triangle thing happening here, right? So this is not just going to be nice and perpendicular. So we're going to start defining some things. So first we want to indicate the direction of the magnetic field. So this better not be different than what we've been doing in the past, because we've been doing problems like this for a while. And of course, if I just stick my thumb to the right and pop my fingers up, they come out of the page at the top and wrap into the page at the bottom. So B is out of the page up here, and it's into the page down here. So it's going to be out, and nothing we can do is going to change that no matter where I am at the wire. I'm literally just shifting my hand, and it's still popping out of the page up there. All right, so magnetic field is, of course, out of the page. And once again, we do not need components because all dBs are out of page. All right, of course, now we got to derive our expressions for r squared and sine theta. So, well, we got ourselves a nice little triangle here, so it's time to define some quantities. So let's call x the distance from the midpoint. So we're going to call this x. And of course, if we have the two legs, we can use our good friend Pythagoras to get the hypotenuse length. So that sets up our triangle. And now we can see that r squared is just going to be the hypotenuse squared. So square root x squared plus a squared all squared, which is of course x squared plus a squared. And sine theta, by definition, is opposite divided by hypotenuse. And the opposite side of our triangle is a. And our hypotenuse is, of course, the Pythagorean distance. So hopefully we're starting to see that this is going to work out very similar to our case of the electric field from a line of charge, because we're going to get a very similar thing happening. Because that one had an r squared and a sine theta, but for a different reason. So we're going to build our integral and verify we get the expected result in a long wire case. So We know that b is equal to mu naught I over 4 pi times the integral of sine theta dl divided by r squared. So what is that? Well, first of all, for our integration limits, x is my integration variable I've chosen, and x can be half the wire length left, or it could be half the wire length to the right, because we're at that bisector. So I'm going to range from negative L over 2 to L over 2. Sine theta is that a divided by square root x squared plus a squared quantity, opposite over hypotenuse. Our dl is just dx, and then r squared is the square of the Pythagorean distance. Okay, so now we can simplify, and we do get a familiar looking integral, because we get the a can come out as well. So we get mu naught IA over 4 pi times the integral from negative L over 2 to L over 2 of, we have x squared plus a squared to the 1, and then we tack on the same thing to the 1/2 power, so we have 1 plus a half, which makes 3 halves. And now we're going to look at the limit of the long wire, because this is not a nice integral, right? This is going to be something very nasty to figure out by hand. It's actually not that terrible of a looking antiderivative, but to do it is annoying. But for those that are really interested, I would say substitute x is equal to a times tan theta is usually the first step you do. So we want a long wire. What is a long wire? So long or infinite means that we can say, in comparison to this distance L, A is really small, so the wire is infinite, right? Even if I take this little pen and if I put it right up to my eyes, all I see in my vision is pen. So if our distance of observation is very small, that means we can approximate this length as infinite. And we do that because this infinite integral has a really nice clean value. And it's given to us possibly useful results. And of course, if I put it there, it's not possibly useful. It's actually useful. So this means that B is equal to mu naught I A over 4 pi times 2 divided by a squared was what I told you the integral evaluates to. If you type it into Wolfram Alpha, you'll get that. And what do we see? Well, one of the 2 cancels with one of the 2's in the denominator, so the 4 becomes a 2, and the a cancels in the numerator, so we get mu naught I over 2 pi a. And of course, whenever we prove something we would like, we get to sound very smart by putting as expected. So that's the long wire case. And just like we had a quick trick with Gauss's law to get the line result really quickly, we'll have a way to do it for the B field as well, using Ampere's law. And now to conclude, we have an interesting case study. It's definitely in the E&M curriculum, but this is not something I imagine seeing very often. It does involve some cool things, and it's not terrible, so we'll do it. So lastly, we're going to use our current loop. So remember, we said B at the center of a loop was mu naught I over 2r. So what if instead of being at the center of the loop, we're displaced some distance above its central axis? So this should bring some memories back for a few sections ago when we did the ring of charge. We'll have some ideas as to what are going on here. So this is one that's kind of interesting. So let's consider just any random current segment. I'm actually going to pick the one that's running into the page right here. So I'm going to pick this as my little current segment. the one that runs into the page. And let's try to actually draw sort of what's going to happen here. So first of all, we know for sure that this is that Pythagorean distance again. So what's the field going to do? So again, if we remember, we know it curls around, the magnetic field curls around and circulates around these current segments. And this one, we should use our tangent trick where if you draw the r vector to the point, it's going to be perpendicular. And if you sort of sweep using your fingers and your thumb as the field, we see that we get sort of this cone shape that gets traced around. And it's not totally into the page or out of the page. My thumb actually traces out this cone shape when I do this. So what we'd actually get is from this particular current segment, our B field we generate is going to be this. So that's actually our little dB. Because again, we know it's going to be at a 90-degree angle, and it's going to circulate this way. So this is the one case of Biot-Savart that actually requires components. Because we see that if I sweep my thumb all the way around, sort of mocking that current flow, we see that my thumb always sticks somewhat up, but all of the other parts cancel. So the parts in the sort of plane of the ring are going to cancel. So what we actually want, because if you think about this current segment over here, if we think about drawing a mirror current segment over there to really show kind of the cone design, we see that by symmetry, we can always find a component that is going to cancel it horizontally. So what we want is we're actually interested in this sort of upwards component. So our net B field is actually going to be in the Z direction, which makes sense because when we had a current loop, the B field perfectly penetrated the center of that loop in some direction depending on which way the current was flowing. So it makes sense it's going to be that way. So here is a case where we need some trig. And it's not necessarily the most straightforward thing. So we know that we want this sort of vertical component. So we want the sine of this little angle phi. And I'm calling it phi and not theta because this isn't the theta we want in our problem. Theta is the angle between the blue and green vectors, which is going to be 90 degrees. Because we have the blue vector that's into the screen and this green vector that's entirely in the plane of the screen. So on the figure above, draw the segment. We already did that. Indicate the direction of the net magnetic field. So B is upwards, which is in the positive Z direction. Are components required for this problem? Yes, because we see that the dBs sort of trace out a cone. So which means that the sort of horizontal components cancel. So we actually will need a component maker. We got to figure out where this angle goes. R squared and sine theta, not difficult, because of course, we're still living in the land of Pythagorean theorem, so got ourselves a nice right triangle here. So r squared is once again that Pythagorean distance. And sine theta is equal to sine of 90 degrees, which is 1. So I think we should justify that because that's not really clear. So theta is the angle between the current segment and r. It is not any of these triangle angles. So we have to look at our current segment and our green vector. So again, that's because this was this was our current segment, IDL, and this was our R vector. So we see that it's entirely perpendicular because R existed in an entirely different plane as this DL. It's actually easier if you think of the dot product definition, right? This would only have a Z component, and this doesn't have a Z component, so there's no way these can't be perpendicular. All right, so B is equal to mu naught I over 4 pi times the integral of dl sine theta over r squared, but we actually do want a component. So just like we had to tack on a component maker when we dealt with E fields that partially canceled, here we have to tack on a component here. So we also need to tack on not just a sine theta, but also a sine phi, and we'll deal with that shortly. So mu naught I over 4 pi times the integral of dl sine of 90 degrees is 1. R was the Pythagorean distance. And what is sine of phi? So this is the one thing about the ring, one of many things. It makes us like very non-trivial, is we have to figure out where this sort of angle phi goes. So this entirely relies on the fact that this is a 90-degree angle at this meeting point right here, that this is a 90 degree. So you could do some alternate interior shenanigans for those of us that are trigonometrically inclined, or just remember your geometry rules. I typically don't. So I just try to find my right angles and go from there. So this is a 90-degree angle, this junction right here. So if this part is phi, this part is the complement of phi. Maybe I should use a different color. I'm quickly running out of colors, so we'll use blue. So this little blue arc is going to be 90 minus phi. But by the same argument, we can form another 90-degree angle. So that's going to mean that this angle in the corner right here is also going to be phi, because we're just cycling through phi and its complement. So that angle goes right there. There's another argument we could do with alternate interior angles. You can explore that one as well. Because what I would do for that, remember alternate interior angles form a Z. So if I formed a Z shape like this, that would tell me that this angle is going to be the same as this angle, which is going to be phi's complement. So phi goes in the other spot. So actually, some of the hardest part of this problem is its geometry. Well, the entire difficulty is the geometry, because we're dealing in 3 dimensions. So what is sine phi? Well, opposite over hypotenuse, it's pointing at the r vector. So we get this. Because the opposite side, the one it wasn't touching, was r. So we get mu naught I over 4 pi times the integral. We can pull out the r of dl over, we get the 3/2 power again for the same reason. But z and r are both constants, just like it was for the ring of charge. So actually everybody's a constant, so everybody gets pulled out. Mu naught IR over 4 pi times z squared plus r squared to the 3/2, and then we're just integrating dl. So if I integrate all my length around the ring, how much length have I gained? Well, once again, it's going to be 2 pi r. So we get mu naught IR over 4 pi times z squared plus r squared to the 3/2 times 2 pi r. And let's see what that is. Well, the 2 pi is going to partially cancel the denominator, and I get an extra r. So I get mu naught IR squared divided by 2 times the quantity z squared plus r squared to the 3/2. And now let's check this. So we have one very special case of this problem, and that's the case at the center. So we know what b from a loop should be at the center. So our field at z equals 0 better be that. So let's check. When z equals 0, I can't draw a straight line. When z equals 0, b is equal to mu naught ir squared divided by 2 times 0 squared plus r squared to the 3/2. And of course, the 0 doesn't affect anything. So this is just going to give us mu naught I squared r divided by 2 times r squared to the 3/2. Forgot my square. I put my square on the wrong thing here. And then remember what it means to be a 3/2 power. So the 1/2 cancels with the 2, so I get an r cubed on the bottom. So I get mu naught I r squared over 2r cubed. And just like magic, those two r's cancel, so I get mu naught I over 2r as expected. That is a tough one. Do I expect us to see the ring of charge? Or sorry, ring of current? No. Should we be able to handle it? Probably. But that's my notes. So I would say the loops and the wire is much more important than this ring, but we only did 3 problems before it, so I think we could handle a little bit of an extension at the end here. So that's Biot-Savart. So next time we'll look at how to compute some of these fields without having to actually integrate.